In the previous episode, I showed you how to derive dual model for a given linear programming model. And this was a particular type of model with given numbers. So what I want to show in this episode is how to do this in a more general way. So what I want you to observe here is, first of all, we had a maximization problem. We had resource constraints or less than or equal constraints. And we had non-negativities. This is x1, this is x2. Sorry, it's not very clear, right? And what we did is we created a problem that had what? That had, instead of maximization, there was a minimization. The number of variables, there was one variable for every constraint in the original problem. There was one constraint for every original variable. For x1, for x2, there were constraints. First constraint, second constraint. The variables were also non-negative, but the constraints were greater than or equal to 0. And what I want you to recall is that the objective coefficients in the original problem became right-hand sides in the new problem. The right-hand side values in the original problem became objective coefficients in the dual. And then the matrix of coefficients, 1, 1, 9, 6, 12, 16, became also the matrix of coefficients, but it was transposed, right? It's 1, 1 in the columns, where it was in the rows. 9, 6, and 12, 16. What was in the rows of the original matrix of coefficients became transposed. So how can we define a dual problem in general? Let me just scroll this a little bit higher. Get this out of the way. So basically, if we have any problem, any linear problem, which we will call primal problem, primal, right? This problem will be defined as maximize in a matrix or vector and using matrices and vectors C transpose X subject to, right? There is the matrix of coefficients multiplied by vector of variables less than or equal b, and x greater than or equal to 0. If this is a primal problem, there's going to be an equivalent dual problem, right? Both of those are LP problems, right? We are all the time in linear programming, right? This will be minimized, and like I said, what was on the right-hand side becomes objective coefficients. B transpose y, there are new variables y, and this will be subject to, and the constraints, right, the matrix of coefficients is transposed, so we can say A transpose times y, and then they were less than or equal, the constraints become greater than or equal times, greater than equal. And then the right-hand sides are what was originally objective coefficients, and then y is greater than or equal to 0. So, right, the first thing that we want to say is this is when we have the less than or equal constraints and maximization, that's what we do. So we can always transfer a problem easily to maximization, but sometimes we have equality constraints, and how do we deal with them? We could convert them to inequalities, right? But there's an easier version. We can say that, okay, whenever we have a primal problem, we turn it to maximization, and then the dual will always be a minimization, right? Now, if the constraints are, if the constraints, if they are less than or equal constraints, then the corresponding variables will be greater than or equal to 0, right? So constraint is something less than or equal bi, right? Then the corresponding variable yi will be greater than or equal to 0, right? So this is what we see here. There's a less than or equal constraint, all of them. Then therefore, the y variables are all non-negative. What happens if the constraint happens to be originally greater than or equal to bi? Well, we can actually have a negative, non-positive variable. We could say less than or equal to 0. And if the original constraint is, it's equal to the bi value, then the corresponding yi variable will be free, right? Meaning, right, it can be any positive or negative or 0, right? They can take any real value, positive, negative, or 0, right? So this is for constraints, and then if the original variable, right? What about the variables? So one thing before we continue, for the constraints, notice that, right, for every constraint in the original problem, there is a y variable associated with it, a dual variable, right? So we're saying for a constraint that was less than or equal, the dual variable will always be greater or equal to 0. For a constraint that's greater than or equal to some right-hand side, the dual variable will be non-positive. It will be negative or 0. And for equality, the dual variable is free, is a free variable. It is either positive, negative, or 0, any value, right? And then if the original variable xi was greater than or equal to 0, then the constraint in the dual that corresponds to this variable will be greater than or equal c. Actually, this should be xj. This would be, the constraint will be, maybe, let me move this a little bit, oops, back. The variable xj, there will be a corresponding constraint indexed by j, and this constraint will also be greater than or equal cj, right? So we remember, right? So in this example, this was the case. The variables were all non-negative, and the constraints were therefore greater than or equal to. If the variable happens to be, rarely, negative or 0, the constraint by analogy should be less than or equal to cj. And if the variable is free, the constraint should be equal to cj, right? So we have these cases, and basically, so if you have a model that, let's say if it has a minimization objective, just negate the objective and make it a maximization. But if you have any constraints or any variables, by this, right, this set of rules that are like in this table, you can write any dual problem for any given linear programming problem, right? Now, what's easy to actually show is that if this is a dual for the primal problem, the dual of the dual is again the primal problem. So if I have a primal problem and I create a dual and then take this problem and create again the dual problem for it, this will actually result in exactly the primal problem again, right? So let's write this. So the dual of the dual is the primal, right? So the dual of the dual is the primal problem. And to see the example of this, right? So if I take this problem that we see here on the right, and I want to create a dual problem for this. So, right, this is minimization. I need it to be maximization. So I'm going to just negate the objective. So, right, let me reformulate. This is the dual problem that we see here, right? This problem, right? So I can turn it into maximization of minus B transpose Y, right? Negating the objective, I make it a maximization, and subject to, and again, I could take these constraints greater than or equal and use negative corresponding variables, but I don't want to create negative variables. I rather transform those constraints into less than or equal. So I'm going to make them minus A transpose Y less than or equal minus C, multiplying by minus 1, by right, negating. All the inequalities change the direction, and Y is still greater than or equal to 0. Now let's apply our rules to formulate a dual for this, right? So So the dual for this, right, if this were the primal now, the dual would be, maybe I should just, let's say, okay, the dual for this is what? I need to take minimization. Now I need to take the right-hand sides, put them in the objective. So the right-hand sides are minus c. I will need to transpose them times some variables, call them y. Let's say I'm creating new variables, right? Dual variables. And then subject to, and I'm going to say the same matrix as here. So it's minus a, and I need to transpose it. But if you transpose a transposition, you basically remove the transposition. So it's minus a times the variables x. And I need to create, right, it was the dual, I need to create greater than or equal. And then the right-hand sides are objective coefficients from this problem, so they'll be minus b, right? And then x is greater than or equal to 0. And it's very easy to see that this is actually now, right, this is the same as saying, right, if I negate again, it will be maximization of C transpose X subject to, and again, negate both sides, it will be AX less than or equal B, and X greater than or equal to 0, right? And you will see this model, this model is exactly the same as our original primal model, right? So what I wanted you to see is that if you create for a model a dual problem, right? We went this way, and we created a dual, and now we took this model, and again, right, so this from here is just copied here. And again, we created a dual problem, right? We obtained, by transforming it, again, the primal, right? So that's what we say. Dual of the dual is the primal problem. Let me clean up a little bit here. Okay, another thing that is very interesting is that is a so-called weak duality theorem. Weak duality theorem, right? And the weak duality theorem says that if X is feasible for, right? Let's call this primal problem P, right? This is problem P, and let's call this D for dual. Right? Is if X is feasible for P and Y as a solution is feasible for D, right, for the dual problem, then we have C transpose X. The objective value of the primal problem is always less than or equal to B transpose Y, right? So what's interesting is that, right, I mean, this is actually easy to see. Since optimal values, we said before, they have to coincide, right? Any feasible solution in the maximization problem will have the optimal value or less. And in the dual, when we're minimizing, any feasible solution will have an optimal value or higher, worse value, right? So this is going to be interesting, right, from the point of view that if you take any dual feasible solution and you calculate its value, it is going to be an upper bound on whatever you can get in the primal, right? Or if you calculate the value in the primal, it's a lower bound on whatever you can calculate in the dual. A stronger theorem, which is called, right, strong duality theorem. The strong duality theorem says that if P, capital P of course, the primal problem has an optimal solution, right? If it has an optimal solution, then so does the dual, right? Right? And, right, let's call this x star, and let's write, say, y star, right? So if the primal has some solution x star and the dual has some solution y star, right? So we're saying if the primal has an optimal solution, then so does the dual. Say the optimal solution of the dual is this, and right, we said this already in the example, but in general it works that the optimal value of the primal is the same as the optimal objective value of the dual problem, right? This is interesting, but there are also other consequences of this, right? For example, we can say what if the primal P is unbounded? If primal is unbounded, right? So we're maximizing, and then the solver says you can increase this objective to infinity, to plus infinity, right? Well, by this we mean, right, even by weak duality, if this can be increased to plus infinity for some, there are solutions like this x, where the objective value can be taken to infinity, then these cannot exist, right? Because nothing can be greater than or equal to infinity. So what we will say is that if primal is unbounded, dual is infeasible, right? So, and then, of course, because there is this symmetry, remember, the dual for the dual is again the primal, right? We could say exactly the same statement if, right, the dual is unbounded, right, then primal is infeasible, right? And, right, but notice, what if primal or if dual is infeasible? What can we say? Can we conclude back that the other one is unbounded? In fact, no. We can say, right, so if primal is infeasible, right, then then the dual is infeasible or unbounded, right? And so, right, and of course I could have written the same sentence, if the dual is infeasible, then the primal must be infeasible or unbounded. So generally, if you consider all possible cases, we can create a table where we say, well, this is the primal problem. It's either optimal or infeasible, or unbounded, right? That's right. Right? And the same thing, we can say the dual could be optimal or infeasible or unbounded, right? There are these cases, right? Like all 3 by 3, if we were to list them, in fact, not all of them are possible. Which ones are possible? Let's understand this, right? So here is a little table of possibilities, right? So which ones are possible? So we said, first of all, right, if one has optimal solution, then so does the other, and their values will coincide. So this is definitely possible, right? We also said if primal is unbounded, this case, then dual must be infeasible. So this case is definitely possible, right? So, and if dual is unbounded, the same thing happens for primal, right? The primal must be infeasible. This is also possible, right? However, right, so basically what we have excluded already is when one is optimal, this is not possible, and this is not possible. And when the other is optimal, right, this is not possible, and this is not possible, right? And when it is unbounded, the other one must be infeasible, so this is also not possible. And this one is unbounded, this one must be infeasible, right? But what about this case? In fact, it is possible. There are example problems which show that, right, that if a problem is infeasible, the dual could be infeasible, but it could also be, it could be unbounded, but it could also be infeasible. Both of them could be infeasible, right? So this is something about duality in general. And of course, you know, I hope with this introduction you can see that we can write a dual problem for any given problem with any given data in the same way, right? But we don't need to do this full transformation that we did in our first segment, where we did the derivation by introducing multipliers and gradually transforming the primal into dual. We can basically use this table that you see here, right, on the right, this table, and say, okay, start with a maximization problem, and for every constraint create appropriate variable, for every variable create an appropriate constraint, whenever, right, and then remember that whenever we're transforming these problems, whatever was in there as objective coefficients become right-hand side values, and whatever were right-hand side values become objective coefficients, and the matrix of constraints needs to be transposed.